So absolute and conditional convergence is actually fairly straightforward. A series converges absolutely if that's true. Okay, so basically it's the absolute value of the series, that convergence thing with absolute convergence. Does that make sense? You're basically looking at the positive series. Okay. A good example of this. Let me see here. Is that series there? Okay, so does this series converge absolutely? So you're going to absolute value that, right? Which is the same as 1 over n squared, because you're just taking the negative out, right? Does that converge? Yeah. B series, B is 2, right? So right. Therefore, that series converges absolutely. Okay. So you just absolute value it. Here's why this is useful. If a series converges absolutely, then the series converges.
Is that the absolute value of the fraction? Is that the absolute value of the fraction right there?
This? Yeah. Basically all you're doing is taking this alternating part off. It makes it positive, right? So this is the only thing it changes, because that's positive the whole way through. So if I can determine this converges, I know that that's going to converge. Right? So if I can slap an absolute value on there and get rid of the negative part, still show it converges, then we know that that converges as well. Okay. So it can be handy, all right, in certain instances. It's not really an official test. Absolute convergence is not an official test. But basically what it is it becomes the alternating series test, which I'll show you that in a minute. We already did that one.
So is this kind of a way to simplify it into an easier test?
Yeah, it'll lead us to the alternating series test. So let's talk about conditional convergence real quick, and then we will move into the alternating series test. Okay, conditional convergence is not really something that comes up very much, but it is worth noting. A series converges conditionally if the series converges, but the absolute value diverges. Okay.
What would be an example of that?
I'll have to show you the alternating series test first, and then we'll. All right, so know the difference there. This is basically if something converges absolutely, then it converges, but it does not work backwards, right? So just because something converges here does not mean the absolute value converges, right? So that's that back and forth game we've been talking about a little bit. That would be the converse. The converse is not true. So, all right. The alternating series test is what will show that this, show an example here. So, you remember what an alternating series is? I hope. We're going to assume.
So if the absolute converges, then the rest of it converges. If the absolute diverges, then it doesn't matter.
If the absolute diverges, we can't say anything about the conclusion for the other one. Okay. Does that make sense? Here's what I can say. Okay, if this converges absolutely, then the series converges. If this does not converge, this is a contrapositive. If this does not converge, that does not converge. Absolutely. Okay, those are the two things that I can say. But I cannot say this, the inverse or the converse. Okay. The inverse being if A sub n does not converge absolutely, A sub n does not converge. Don't know that. Or if A sub n converges, then this converges. I can't say that either. So just the contrapositive and the statement. Those are the only two that we can say for sure.
So what's the contrapositive?
The contrapositive is if not this. So if this does not converge, then this does not converge. Right. Switch it and negate it. Yeah, whole theory games. Okay, so for the alternating series test, we're going to have a sequence A sub n that is positive and decreasing. That's not a condition because we're not doing an integral. Like the integral test had continuous in it because we had to change this into a function that was continuous to be able to calculate a definite integral, right? We're not using an integral here, so we don't have to worry about continuity. But you can in your brains lump those two together if you want. Positive and decreasing. Okay. Then so this series, if we make it alternating, see how we have a positive and decreasing sequence and we make it an alternating series? Then we know that that is convergent. Okay. That's it. Yeah. it's a, like I said, it's a pretty handy test. If you see an alternating series, and you can show that sequence is positive and decreasing, good to go. Okay. Again, for example, right here, is that positive and decreasing? And this is an alternating series, therefore it converges. Okay. So this is basically a direct result of the alternating series test. Okay. So that's it. That's all you got to do. Take the I don't think there's anything else. Is there? Look at this series. So we're going to take a look at this sequence, correct? Okay, is that positive for n greater than or equal to 1? Yeah, it's positive. Okay, decreasing? Yeah, it is, because 1, 1/2, 1/3, 1/4, 1/5, right? Okay, since that's an alternating series, it converges. There you go.
So alternating series is always going to converge no matter what.
No,
As long as it's decreasing and.
as long as these two conditions are met,
Okay.
a positive, decreasing sequence, if you make that an alternating series, it converges.
That's just different from the first one we read, where it gets positive decreasing. Was this exact?
That was an integral test, right? So that's just a different method for showing that something converges. The integral test doesn't work with alternating series. Okay, this makes it ugly. Okay, can you, so if you wanted to try to use the integral test here, you'd have you'd have an integral -1 to the x over x. You know how to solve that. Because that's, first of all, is this continuous? Well, for it, it's greater than 1, so we don't have to worry about 0. What happens if I have an exponent of 1? It makes it negative. And I change to an exponent of 2, makes it positive. There's going to be a jump. Okay. So between like 1.99999 and 2, you're going to have a gap. That's not continuous, we can't use the integral test. Right. So there you go. Alternating series test. Very handy. Okay, good. All right. So here, let's take a look at this series. Okay, first thing you notice, it's an alternating series, right? So we're in an alternating series. And then we take a look at what sequence. n. Okay, is that positive for n greater than 1? Yes, it's positive. Is it decreasing? Yeah, it is. Okay. So by the alternating series test, does that converge? Yeah, okay.
So for the numerator, whatever's in the power position, does that even matter?
Well, n or n plus 1, all it does is changes the first term from negative to positive. Right? So if this is -1 to the n plus 1, term 1 is positive, because it's n negative 1 squared. Versus if it's to the n, the first term is negative. It's -1 to the 1. Right?
What if it was n squared?
Then, let's see, it's gonna still, so 1 squared, term 1 is 1 squared, which is 1, odd. It's still gonna alternate, because 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, yeah, they alternate anyways, so even, it's all you have to look at is even or odd, and that determines sign. Okay, so the alternating series converges, right? But let's look at the, let's determine absolute convergence here. Does that series converge? Why? Yep, it's a p series, p equal to a half, right? So we have a series that converges, but does not converge absolutely. Okay, so does not converge.
So just because
Absolutely.
it's an alternating series, it makes it convergent?
Yeah. Okay, so we would call this series right here is what we would call conditionally convergent. Okay. So it doesn't converge absolutely, but it does converge. We call that conditional convergence. Okay. That's the question. That's what you're asking for. Let me show you a picture of why that works. Like, so for this series, your first term is positive, right? So your sums are going to start there. And what's our next term going to be? Negative, right? So we're going to subtract out of there. So basically what you're doing is the sequence is I should write that differently. So negative and then a positive and then a negative. And see how the sequence gets smaller and smaller? Okay. The sequence is going towards 0, right? The sum is going to have an upper bound, and that's why it converges. Okay. It's because those negatives take out enough values that it will converge. The sums will converge to some value up top. Right, so that's why the alternating series works. But even though this series may not work as convergent. All right. That's it. A little shorter today. Any questions? All right.
Will you ever be asked to prove if it's conditionally convergent on a test, or is that?
I'm pretty sure the AP doesn't worry about that. It's one of those little things that you'd need to know from college, right? So I throw it in. Yeah, I'll make sure, but I'm pretty sure they don't worry about it. They're more concerned with the alternating series test being used, right? We'll check this tomorrow. So that's the only one-day assignment in our section here.
Where you think
Fantastic. What's wrong? You having trouble looking at that scoreboard? I intended on switching that, but I just never have. Okay, ratio and root test tomorrow. And then next week we look at Taylor series and power series.
What ratio and root test, what is that?
It's just two more ways to determine convergence. Yeah.
I thought, like, do we have a curriculum on